So now let us try to understand what are called properties of eigenvalues. In the example that we had done till now, remember those things. There we had shown that if lambda 1 and lambda 2 are eigenvalues, it was for 2 cross 2 matrices if you remember, then lambda 1 plus lambda 2 was nothing but trace of A and their product was nothing but the determinant of A. Alright. Now, we would like to prove this result for the general setup that indeed it is true. Fine. So, let us look at A, whatever we have. So, A is some A11, A12, A1n, A21, A22, A2n, AN1, AN2, ANN. Let us compute determinant of lambda I minus A. So, what is the determinant of lambda I minus A? It is nothing but determinant of lambda minus A11 minus A12 minus A1n minus A21 lambda minus A22 minus A2n minus AN1 minus AN2 and lambda minus ANN. So, this is what I have. What we know is that this is a polynomial. So, look at the diagonal here, the main diagonal. So, look at the main diagonal. Lambda appears n times and therefore, it is a polynomial in lambda of degree n. That we had said earlier also. I did not do it, I just made a statement. So, you can see here that lambda, so if I look at this, it corresponds to looking at lambda minus A11 times lambda minus ANN plus n factorial minus 1 more terms, all right. So, when we compute the determinant, there are n factorial terms. Out of those n factorial terms, I have one term which is this, which corresponds to the main diagonal, and then there are other terms also which are playing a role here as far as the determinant is concerned. So, since it is lambda minus A11 lambda and lambda minus ANN, this itself is a polynomial of degree n and therefore, I will have degree n polynomial. Fine. So, a polynomial of degree n, hence over complex numbers, hence over C, it will have n roots, say lambda 1, lambda 2, lambda n. Fine. They may be distinct, but they may not be distinct, that I am not bothered about, but they will have n roots. Once I have n roots, what we are saying is that if I look at determinant of lambda I minus A, this was nothing but the characteristic polynomial. Fine. There was a notation for characteristic polynomial. So, I can write this as, since these are the roots, I can write this as lambda minus lambda I or lambda minus lambda 1 into lambda minus lambda 2 till lambda minus lambda n. I can write like this, because those are the roots. And look at the coefficient of lambda to the power n, coefficient of lambda to the power n, coefficient of lambda to the power n here is 1, and the same thing is true here also, that coefficient of lambda to the power n is 1, and hence everything makes sense, there is no problem here. We generally write it in terms of product lambda minus lambda I is equal to 1 to n. In my notes and everywhere, this is the way we write. So, the idea is to understand the two things. The left hand side is this expression which is quite long, the right hand side is just a polynomial which has been factored into linear factor, which has been factored. So, there are two terms and from there I want to build up my ideas, all right. So, let us try to do that part, let us try to understand. So, first thing is, what about trace of A? How do I get trace of A? So, what we know is that trace of A is nothing but A11 plus A22 plus ANN, all right. Now, where does that term appear? So, if I look at this, this thing appears at this place. Look at the main diagonal here, look at the main diagonal, fine. Look at coefficient of lambda to the power n minus 1. So, this appears in coefficient of lambda to the power n minus 1 of lambda minus a11, lambda minus a22, so on till lambda minus a n. All right, fine. And there is no other term of lambda to the power n minus 1. Why? Because if I do not want a term of lambda to the power, so if I look at this part, the main diagonal gives me lambda to the power n, lambda to the power n minus 1, lambda to the power n minus 2 and so on, fine. If I do not want to look at the main diagonal, if I want to look at any other thing, all right. So, as soon as I look at any other term here, for example, if I want to look at any term here, then this tells me that I will have to remove this row and I will have to remove this column. This is what the determinant was. Determinant means if I am looking at there is a term aij, I not equal to j, it means that need to remove the ith row and jth column. Now, if I want to remove ith row and jth column, it means that jth column means this will give me lambda minus aj, j will get cancelled out, and from here I will get lambda minus aii cancelled out, all right. So, one of them will always get cancelled out. This is what you have to understand. So, when I want to compute the determinant has n factorial terms. Out of that, there are what are called the main diagonal and the rest are n factorial minus 1 terms. If I look at this n factorial minus 1 terms, lambda to the power n minus 1 does not appear. So, lambda to the power n minus 1 does not appear. Why? Basically because I will get some aij, and that aij, and there I know that I is not equal to j, there will be at least one term aij which is I is not equal to j, and that will get rid of lambda minus aii as well as lambda minus ajj, and therefore, there will be only lambda to the power n minus 2 terms, at most lambda to the power n minus 2 terms. So, any other non-diagonal element, so any other term here, so this term, so any term which is not the main diagonal contributes at most lambda to the power n minus 2, coefficient of lambda to the power n minus 2. It won't give me lambda to the power n or lambda to the power n minus 1. Is that okay? So, let us go back now. So, I am looking at trace of A is this. So, this is same thing as looking at appears in the coefficient of lambda to the power n minus 1, which is this. And how does it come? So, if you look at lambda to the power n minus 1, the term here is coefficient of lambda to the power n minus 1 in determinant of a minus lambda I minus a, I wrote lambda I minus a is nothing but minus of a11 plus a22 plus ann. Look at here, fine. Why it is happening? So, let me write that nicely, maybe there will be some clarity. So, I want to look at lambda minus a11, lambda minus a22 and lambda minus a33. Then I would like you to see that this is nothing but lambda cube minus lambda square times a11 plus a22 plus a33 plus lambda times a11 a22 plus a11 a33 plus a22 a33, all right, minus a11 a22 a33, all right. This is what we have. So, basically what we are saying is that any polynomial, if these are the roots, a11 alpha beta gamma are the roots. So, if alpha beta gamma are the roots, if so, no, I should have written x minus alpha, x minus beta, x minus gamma, then this corresponds to x cube minus alpha plus beta plus gamma times x square plus alpha beta plus alpha gamma plus beta gamma times x minus alpha beta gamma. This is what we are writing here, nothing else. Fine. So, what we see is that I have got this part, coefficient of lambda to the power n is this, but what we are saying here is, understand carefully, there should not be a confusion, that I am writing determinant also as like this. Fine. So, I think I should go to the next page for clarity. So, what we have taken is determinant of lambda I minus a. One way, this is nothing but the characteristic polynomial. We wrote it as product I going from 1 to n, lambda minus lambda I, which is same as lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda n. This was one term of this was lambda minus a11, a22, lambda minus ann plus n factorial minus 1 other terms. This is what we had, all right. So, in this I am looking at, so look at coefficient of lambda to the power n minus 1 on both the sides, on both sides. So, on the left hand side, if I look at left hand side, as I said, lambda to the power n minus 1, so lambda to the power n minus 1 appears only in lambda minus a11, lambda minus a22, lambda minus ann, and this gives me coefficient of lambda to the power n minus 1 as minus of a11 plus a22 plus ann, all right. If I look at the right hand side is basically this itself, and therefore, this will give me coefficient of lambda to the power n minus 1 as minus of lambda 1 plus lambda 2 plus lambda n, fine. And therefore, I know that this is nothing of a, so this will be same as this. This minus sign and this minus sign, they cancel out, all right, negative sign cancels, fine. So, therefore, what I get is that trace of a is nothing but sum of the eigenvalues. Fine. What about the determinant? Let us look at determinant of A. So, if I want to get the determinant of A, I need to substitute lambda equal to 0 here, all right. So, if I substitute lambda equal to 0, what I get is, so substitute lambda is equal to 0 to get P0 is equal to determinant of minus A, which is same as minus 1 to the power n into determinant of A. Why minus 1 to the power n? Because this matrix is of size n cross n, all right. So, I am multiplying by a scalar minus 1, so that gets multiplied, fine. What about the right hand side? Look at the right hand side, right hand side is nothing but 0 minus lambda 1, 0 minus lambda 2, 0 minus lambda n, which is same as minus 1 to the power n lambda 1, lambda 2, lambda n, and therefore, I get that minus 1 to the power n minus 1 to the power n cancels out. I get determinant of A is nothing but lambda 1, lambda 2, lambda n, fine. So, we have shown that trace of A is same as sum of the eigenvalues, and determinant is nothing but the product of eigenvalues. It is a very important idea, it helps us at lot of places. There are other things also, you can go for 2 by 2, 3 by 3 and so on, but that is not in our syllabus. Our syllabus is only about trace and determinant. So, you need to keep track of that, fine. Now, let us look at what are called algebraic multiplicity and things like that. So, let me go into the next idea. So, let us concentrate on a spectrum of a matrix. So, a spectrum means eigenvalues. So, fine. Then there is a notion of what are called now algebraic multiplicity. multiplicity, and there is a notion what is called geometric multiplicity. So, algebraic geometric multiplicity of what? Eigenvalues of this. All right. So, let lambda be an eigenvalue of A. Recall we are doing everything over complex numbers. So, let lambda be an eigenvalue of A. This is the assumption. Then there is notion of algebraic multiplicity of lambda as an eigenvalue of A. So, this is the multiplicity of lambda as a root of the characteristic polynomial determinant of xi minus a. So, this is a polynomial of degree n, polynomial degree n, fine. And what is the geometric multiplicity? This is the corresponds to dimension of null space of lambda I am looking at. So, it is either you can write lambda I minus a null space of this, or same as dimension of null space of a minus lambda I, whichever you are comfortable with, you are supposed to look at this. So, geometric multiplicity is the dimension, fine. So, let us take an example to understand it so that I can proceed further. So, example. So, let me take one example. I define A as 1 1 0 0 1 1 0 0 1. I look at this, all right, fine. So, I want to compute determinant of xi minus a, which is same as determinant of x minus 1 0 0 x minus 1 0 0 x minus 1. So, this is an upper triangular matrix. So, determinant of this is x minus 1 to the power 3. So, this implies algebraic multiplicity of 1 as an eigenvalue of A is 3, fine, because 1 is repeated thrice, fine. What about the geometric multiplicity? For the geometric multiplicity, I need to compute this null space. So, let us compute the dimension of the null space. So, we want to compute, so we want to look at geometric multiplicity of 1 here, all right. So, this is equal to what? So, let us do that out. So, I need to look at null space of lambda is 1 here. So, I am supposed to look at I minus a, null space of this. So, this corresponds to looking at, just have a look at it, 1 minus a. So, this corresponds to the matrix, replace x by 1 here. So, if I do that, 1 minus 1 is 0, minus 1 0, 0 0 minus 1 0 0 0, all right. So, this is the matrix that I am looking at. Now, the rank of this matrix is 2, rank of I minus a is 2. This implies dimension of null space of A will be equal to 3 minus the rank of I minus a by the rank nullity theorem, which is 1, all right. So, the geometric multiplicity is 1. Is that okay? Try that out yourself. Another example. So, another form of this was already given to you earlier. I will write it now with 3 here, 1 here, 0, 0, 3, 1, 0, 0, 3. I look at this, fine. And again I look at say 3, 1, 0, 3, 2, 1, 0, 0, 2, 1, 0, 0, 0 or 0, 0, 2. Suppose I look at this matrix, huge matrix for us, fine. So, all these entries are 0 for us, fine. So, I would like you to see that this is an upper triangular matrix. So, the eigenvalues, a spectrum of A here consists of 3, 3, 3, 3, 3, 5 times, 3 plus 3, 3 plus 2 and 2 appears 3 times. So, this is a spectrum of A, fine. algebraic multiplicity of 3 as an eigenvalue of A is 3 plus 2 is 5. Algebraic multiplicity of 2 as an eigenvalue of A is 3. What about the geometric multiplicity? Check that the geometric multiplicity of 5 of 3 as an eigenvalue of as an eigenvector here will be equal to. So, this will give me, look at the previous example. If you use the previous example, the rank of this, so if I look at this whole part A, I want to look at the rank of that part. So, I want to compute rank of 3i minus A. If I look at that part, what will happen is this will become 0, this will become 0, this will become 0. So, the top one gives me only rank 2, this is 0, this is 0, so it gives me one more rank. So, rank is 3, 1, 2, 3, rank is 3. What about here? Here I will get 3 minus I, so it will get 3 minus 2 is 1, again 3 minus 2 is 1, again 1 here. So, this will give me full rank 3. So, rank is 3 plus 1 is 4, 5 and 6. So, rank of this is 6. This matrix is of size, what is the size of this matrix? 3 plus 3 is 6 plus 2 8. So, 8 minus 6 which is 2, alright. So, the geometric multiplicity of this is 2. If you look at geometric multiplicity of 2 here will be equal to 8 minus, now I need to remove, so I need to look at now 2 here, 2, so 2 minus that, 2 minus 3 will be minus 1, fine, or let me look at 3 minus, so let me look at A minus 2i. If I look at A minus 2i, I will look at 3 minus 2 is 1, 1 here, then 0, 1, 1, 0, 0, 1. This is the first part. Second block will give me 1, 1, 0, 1, and the last part will give me 0, 1, 0, 0, 0, 1, 0, 0, 0, all right, fine. So, therefore, if I see the rank of this matrix is 3 plus 2 5 plus 1 6 plus 1 7. So, 8 minus 7 which is 1, fine. So, I have certain issues that you can see here, that this matrix is not a diagonal matrix, and what we see here is that, look at the previous examples also, our matrix whenever it was not a diagonal matrix, fine. So, this number is not same as this number. Algebraic multiplicity is 5, geometric multiplicity is 2, algebraic multiplicity is 3, geometric multiplicity is 1. Look at previous examples also wherever we have looked at, fine. Look at this here, here it is a diagonal matrix. So, algebraic multiplicity is same as the geometric multiplicity, because there one was repeated 3 and I had 3 linearly independent eigenvectors. Look at here, fine, here and I have only one eigenvector, fine, and this is not an example of a diagonal matrix, fine. So, we will come across all these ideas in the next class, fine. So, I will like you to understand them, which are very important. Now, so let me just do something now as the last part of this part. All right, let me do this, what are called similar matrix definition. So, A is n cross n, B is n cross n, then A and B are said to be similar if there exists an invertible matrix S such that SA S inverse is B, all right. Or recall that I can write this as, which is same thing as writing, already I should have written S inverse here, I think, and S here, AS is equal to SB. It is the same thing because you are just changing them. We are saying that A of S is same as S of B. Think of S, so take the columns of S as ordered basis of Cn over C, fine. Then what we are saying is that I have got A here, I am applying, so S is there, so I am applying A to the first column, A to the second column, and so on, A to the nth column, I am looking at this, and then I am saying that this is same as S times B. So now I am looking at the other way around, the column wise. All right, so you can write it again like this itself in terms of B, in terms of B. Fine, this is what it is. But if B is a diagonal matrix, then RHS has a nice form. RHS has the form. All right, so S I am looking at the first column, the second column, the nth column, and then I am multiplying by a diagonal matrix, say D1, D2, Dn, 0 here, 0 here. Then D1, so this first column is getting multiplied to the first one, second to the second, and so on. So this corresponds to D1 times S of this, D2 times S of this, and Dn times S of this. Fine. So look at this. In general, if I am looking at just any B, I do not get anything. All right. It is just an expression AS is equal to SB, and that appeared at the time of looking at matrix of the linear transform, composition of matrices, and we said that we need to understand that to talk of similarity operation. All right. Here what we are saying here is that in this case, if B is a diagonal matrix, if B is diagonal, then what we are saying is that look at this part, it says that the first column is nothing but an eigenvector. So this gives me eigenpair D1 and this. Recall that any invertible matrix cannot have a 0 vector inside it. So S is a non-zero vector. Not only that, since S is invertible, all these columns are linearly independent. So we have got n linearly independent eigenvectors. So we have got n linearly independent eigenvectors. All right. So I would like you to keep track of that. Further, in general, what we are saying here is that in general, we are saying that S inverse AS is B. So let us look at the trace. What is trace of S inverse AS? Which is same as trace of B. All right. So this is same as trace of, I can interchange. So what we know is that trace of AB is same as trace of BA. Fine, that we had seen earlier. So this is same as trace of AS into S inverse, which is same as trace of AS S inverse. All right. Fine, which is same as trace of A. So when I do similarity transformation, the trace does not change. Fine. So trace does not change under similarity transformation. What about the determinant? Because we had computed the determinant also. So what is determinant of B? Determinant of B is same as determinant of S inverse AS. I know that determinant of AB is same as determinant of A into determinant of B. Determinant of AB is same as determinant of A into determinant of B. So let us do that. So determinant of S inverse into determinant of A into determinant of S, which is same as determinant of A. Fine, because determinant of S inverse is 1. All right. Fine. So you can see that under similarity transformation, the trace and determinant does not change. What can we say about eigenvalues also? That the under eigenvalues things will be the same. All right. So I would like you to check that under determinant, under similarity. So under similarity, eigenvalues do not change. Why it does not change? Because we compute determinant of, why? Because to compute, we need to compute determinant of B minus xi, which is same as determinant of B is S inverse AS minus xi, which is same as determinant of S inverse A minus xi into S. Just multiply x inverse As minus x inverse again. So, you will get back this, which by the same argument as above, it gives me determinant of A minus xi, all right. So, therefore, the eigenvalues will remain the same, eigenvectors will change. We will go back to this again in the next class. That is all for now.